These are your 6-2 notes on inverse functions and relations. We're going to concentrate on 3 objectives in this lesson. We're going to find the inverse of a discrete function that would be like a set of ordered pairs that ends like below. And then we will find the inverse of a continuous function that would be like an equation. And then we'll also have a tool to figure out if given 2 equations, if they're inverses or not. So before we begin all that, let's do a little bit of review on some terminology. So a relation is a set of ordered pairs. A set of ordered pairs can be discrete, and what I mean by that is that they're separate. We don't connect these. This relation only has 2 ordered pairs in it. Or a relation could be a set of ordered pairs that's defined by an equation. The equation would be a line, and so the set of ordered pairs are all the ordered pairs that fall in that line. So it's infinite, it's continuous. We include whole numbers, decimals, fractions, all of those numbers. So we're going to talk about both of those relations in this section. The domain is the set of all first coordinates in a relation. That's your x values. The range is the set of all second coordinates, or your y values. And then the inverse relation is just flip-flopping your x's and your y's. So the inverse is the function or the relation that is in the form y comma x. A function is a special type of relation. It's a relation where the domain does not repeat. So as long as the x value is only there one time, it's a function. So if you look at the example here, the relation R is 1, 2, 3, 4, 5, 6. The domain would be 1, 3, and 5, the set of numbers, the x values. The range is the set of the y values, 2, 4, and 6. And then the inverse relation would be the ordered pairs 2, 1, 4, 3, and 6, 5. And that's just the flip-flop of the x and y. Below I asked the question, is the relation a function? The answer is yes, because the domain did not repeat. There was a separate domain for each range. And is the inverse a function? And the answer here is yes, because the domain of the inverse did not repeat, which is really the range of the original relation. Those 2 things, you could have yes, yes, you could have yes, no, you could have no, yes, you could have no and no. They're completely independent from each other. It just has to depend on, does the domain repeat or does the range repeat, whether or not it's a function or if the inverse is a function. So actually, the very first objective has been met. We have a set of ordered pairs, 1, 2, 3, 4, 5, 6, and I showed you how to write the inverse of those ordered pairs. You just flip-flop them. So that's the first thing that we learned, was how to write the inverse of a discrete set of ordered pairs. The second thing we're going to talk about, and I'm going to actually go ahead in the slide, if I give you 2 equations, I want to know, are they inverses of each other? Will the one function give me an ordered pair, and will the other one give me the reverse of that ordered pair? That's kind of what we're asking here. And the way we determine if 2 equations are inverses or not is we use the composition of each of those functions. And so the composition is what we did in the previous section. If you find the composition f of g, and then you find the composition of g of f, and they both equal x, then they are inverses of each other. So it's sort of what we did in 6.1b. We plug a function within the other function. We simplify. If it simplifies to just a positive x value, no numbers, then, and both of them do it, then they're inverses of each other. And this is just a little bit of information about terminology. Okay, function notation is f of x. So an inverse notation is f to the -1 of x. -1 we use a lot in math, and it's a symbol for inverse. So you remember when you raise a number to a negative exponent, it will flip it. Well, when you raise it to a -1, it flips it, but it doesn't change the 2. The 2 stays there. So when you have 2 to the -1 power, that's the inverse of 2. It actually equals a half. So we use that -1 power to represent inverse of. Even though the inverse may not be a function, we can still use it. We can just call it a relation. All right, so let's go ahead and try this. So I have 2 functions here. I got to see if they're inverses or not. There's a lot of similarities. I do see the 2's and the 8's. So the first thing I'm going to do is H composition G, which is H of G of X. I just wrote it as nested parentheses. I can see G of X sitting inside the H of X function. So I'm going to take the actual G of X function and plug it into that spot. So I'm going to find H in terms of X minus 8 over 2. And what that function notation means is I'm going to use the H of X function, and wherever I see the variable, I'm going to replace it with X minus 8 over 2. So that's 2 times the quantity, X minus 8 over 2 plus 8. Using order of operations to simplify, the first thing I have to simplify is multiplication. So if I multiply this quantity by 2, but then I divide it by 2, it's like it never happened. So those two operations cancel each other out. So now what I'm left with is an X minus 8 plus an 8. And when you have a negative 8 and a positive 8, they also cancel each other out, and we're left with X. So H composition G simplified to just an X. So that means we have to keep looking to see if these are inverses. If we didn't get X there, we'd be done. So now what we have to do is continue, and we're going to actually find G composition H, which is really G of H of X. So I can see H of X sitting inside the G function. I'm going to take the H of X function and plug it in. So I have G of 2x plus 8. And what that means is I'm going to use the G of X function, and I'm going to plug in 2x plus 8 wherever I see the variable. So what this is going to equal is 2x plus 8 minus 8 all over 2. So you can see that I replaced the x with the H of X function. When I simplify this, rules of simplification says I have to clean up the numerator. So I need to do the positive 8 and negative 8 first. That leaves me with 2x over 2. The 2 simplify to 1, and I'm left with an x. So G composition H also equals x. So because that happened, the answer to the question that was asked, are these inverses? The answer is yes. And I'm just going to put they are inverses so you know what we're saying yes to. The proof is in the compositions. So the most work you'll have to show is 2 compositions. The least amount is if you get one of them not to equal x, then you can say no. All right, so the third objective is what if I didn't give you 2, I only gave you one function, and we had to find that second equation. So to find an inverse, we're going to replace f of x with y. That's just sort of an ease of the problem. F of x and y are the same thing. We want to replace x's and y's, so we want to bring a y into the problem. We're going to interchange the x and y variables. We're going to solve for the new y, get y all by itself. And then we're going to check our answer. We can either do the composition thing we just did, or we can graph. We're actually going to graph these. We're going to graph 3 things. We're going to graph the function, the original function. We're going to graph the inverse that you find, and then we're going to graph the identity function. Now, the identity function is the equation y equals x. Graphs of functions and their inverses are symmetrical to the line of the identity function, f of x equals x. So just to review what that identity function is, we talked about it way back in chapter 2. I'm going to show you 3 scenarios that might occur. So the identity is when you plug in x, it gives you the same y value. So that's 0, 0, 1, 1, 2, 2, all the way in the positive 45, negative 1, negative 1, negative 2, negative 2, all the way through. So this is the 45-degree identity function. That's y equals x. And what's nice about it is every function and its inverse is symmetrical around that line. So maybe we have a function here and the inverse here. That may happen where they're parallel. And then if you fold on the blue identity, they're symmetrical. You might have where you have one function here, and then the identity is intersecting here. But again, the identity is symmetrical. You can even have it where it's not even a line and the values still hold true. So I'm just showing you a sketch of a quadratic and its inverse. The identity still cuts it in half. All right, so let's go ahead and try this. We're going to use the function f of x is equal to 2x plus 3. So f of x is equal to 2x plus 3 is the original function. I'm actually going to graph that. So y-intercept is 3. My slope is 2 over 1, so that means to go up 2 over 1, up 2 over 1 to the right, or you could go down 2, 1 to the left, down 2, 1 to the left. So this is the original function that they gave us, y equals 2x plus 3, or f of x equals 2x plus 3. So to find the inverse, I'm going to change that to y equals 2x plus 3. I'm going to interchange x and y, so x equals 2y plus 3. And now I just got to solve for y. I got to get y by itself. So I'm going to subtract 3 from both sides. That leaves me with x minus 3 is equal to 2y. I'm going to divide by 2. Notice when I divided by 2, I divided the x and the negative 3 separately so that I'll have a slope and a y-intercept. If you just draw a line and put divide by 2, it'll be difficult to graph. So y equals 1/2 x minus 3 halves. So the inverse is y equals 1/2 x minus 3 halves. If you wanted to, you could bring in that -1 notation now. The book does that a lot. And so you have the inverse. Regardless, whether you read it with the y or that one, you got a y-intercept of -3 halves. That's -1.5 on the y-axis. And then I have a slope of 1/2. So I'm going to go up 1 over 2. I'm still in the middle of that box. Up 1 takes me to the middle over 2. Or I could go down 1 over 2 to the left. So when I connect and extend, there's my inverse function. And then the third graph I want to add is just the identity. So 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. And -1, -1, -2, -2, all the way down. So it's a 45-degree, just a quick sketch. You can see that the blue identity is this line of symmetry for the red and the green graph. When you fold on that blue line, the red and greens will match up. So it's a quick visual way to see if you're doing it right. Here's your lesson summary. You are going to determine, using composition, whether those two functions are inverses. And then I want you to actually find the inverse of the function f of x is equal to 2x minus 5. You do not have to graph any of these. Good luck.